Can you hear me? I would like to thank you all for coming to my 75th birthday conference. Actually, for those keeping count, I am closer to 75 and a half. But that shouldn't get in the way of a good celebration. Thanks also to the organizing committee and sponsors for making this all happen. In particular, I would like to offer special thanks to Intel, who support our supercomputer, Cosmos, and who have for a long time sponsored development of my communication equipment, allowing me to give this lecture to you today. It is traditional on these occasions to say a few words, and so I hope you will indulge me while I look back over my life in physics and reflect on how our understanding of black holes and the state of the universe has changed. I was 20 in October 1962 when I arrived in Cambridge at DAMT, the Department of Applied Mathematics and Theoretical Physics. I had applied to work with Fred Hoyle, the most famous British astronomer of the time. I say astronomer because cosmology then was hardly recognized as a legitimate field. However, Hoyle had enough students already, so to my great disappointment, I was assigned to Dennis Sharma, of whom I had not heard. But it was just as well I hadn't been a student of Hoyle, because I would have been drawn into defending his steady-state theory, a task which would have been harder than denying global warming. I hadn't done much mathematics in the very easy physics course at Oxford, so Sharma suggested I work on astrophysics. But having been cheated out of working with Hoyle, I wasn't going to do something boring like Faraday rotation. I had come to Cambridge to do cosmology, and cosmology I was determined to do. At that time, cosmology and gravitation were neglected fields that were ripe for development. So I read old textbooks on general relativity and traveled up to hear relativity lectures at King's College London each week. I followed the words and equations, but I didn't really get a good feel for the subject. At that time, it became clear something was not quite right with me. Already in Oxford, I had noticed that I could no longer row a sculling boat properly. The Christmas after arriving in Cambridge, I went home. It was a very cold winter and my mother persuaded me to go skating on the lake in St. Albans, even though I knew I was not up to it. I fell over and had great difficulty getting up again. My mother realized something was wrong and took me to the doctor. I spent weeks in Bart's hospital and had many tests. They never actually told me what was wrong, but I guessed enough to know it was pretty bad, so I didn't want to ask. In fact, the doctor who diagnosed me washed his hands of me, and I never saw him again. He felt that there was nothing that could be done. In effect, my father became my doctor, and it was to him that I turned for advice. At first I became depressed. I seemed to be getting worse pretty rapidly. There didn't seem any point working on my PhD, because I didn't know if I would live long enough to finish it. But then the condition developed more slowly, and I began to make progress in my work. After my expectations had been reduced to zero, every new day became a bonus, and I began to appreciate everything I did have. While there's life, there is hope. And there was also a young woman called Jane, whom I had met at a party. Getting engaged lifted my spirits, and I realized, if we were going to get married, I had to get a job and finish my PhD. I began to work hard, and I enjoyed it. The big question in cosmology in the early 60s was, did the universe have a beginning? Many scientists were instinctively opposed to the idea, because they felt that a point of creation would be a place where science broke down. One would have to appeal to religion and the hand of God to determine how the universe would start off. Two alternative scenarios were therefore put forward. One was the steady-state theory, in which the universe always expanded, and new matter was continually created to keep the density constant on average. By the time I began my research, the steady-state theory was already in trouble with observations, but the final nail in the coffin came with the discovery of a faint background of microwave radiation in 1964. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled, until it is just the faint remnant we observe today. But there was a second alternative to a beginning in time, which is a bouncing, or even cyclic, universe. Perhaps the universe had a previous contracting phase, and that it had bounced from contraction to expansion at a high, but finite density. This was clearly a fundamental question, and it was just what I needed to complete my PhD thesis. Two Soviet scientists, Lifshitz and Kholodnikov, had claimed to have proved that contraction in general relativity without any special symmetry would always lead to a bounce, with the density remaining finite. This result was very convenient for Marxist materialism, because it avoided awkward questions about the creation of the universe. Lifshitz and Kholodnikov were members of the old school in general relativity. That is, they wrote down a massive system of equations and tried to guess a solution. But it wasn't clear that the solution they found was the most general one. A new approach was introduced by Roger Penrose, which didn't require solving the field equations explicitly, just certain general properties, such as that energy is positive and gravity is attractive. Penrose had showed that once a dying star had contracted to a certain radius, there would inevitably be a singularity, a point where space and time came to an end. I realized that similar arguments could be applied to the expansion of the universe. In this case, I could prove there were singularities where spacetime had a beginning. So Lifshitz and Kalatnikov were wrong. General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the eureka moment, shortly after the birth of my daughter, Lucy, while getting into bed, which my disability makes a slow process. The surface of a black hole is called the event horizon. I discovered that the event horizon obeys an area theorem. If general relativity is correct, and the energy of matter is positive, then the area of the event horizon has the property that it always increases when additional matter or radiation falls into the black hole. Moreover, if two black holes collide and merge to form a single black hole, the area of the event horizon around the resulting black hole is greater than the sum of the areas of the event horizons around the original black holes. Along with Brandon Carter and others, I was involved in the proof of the so-called black hole no-hair theorem. We showed that, once a black hole has settled down to equilibrium, it must be described by a solution of general relativity discovered by Roy Kerr in 1963. This shows that classical black holes are very simple objects, described by just two numbers, their mass and angular momentum. The area theorem and no-hair theorem can be tested experimentally by the LIGO Gravitational Wave Observatory. On the 14th of September, 2015, in event GW150914, LIGO, for the first time, detected gravitational waves from the collision and merger of a black hole binary. Since then, LIGO has reported two more detections of black hole mergers. From the gravitational waves emitted as the final black hole settles down to equilibrium, it should be possible to test whether this black hole is described by the Kerr solution, as predicted by the no-hair theorem. From the early part of the waveform, one can estimate the masses and angular momenta of the initial black holes, and by the no-hair theorem, These determine the horizon areas. These can be compared to the area of the final black hole to test the area theorem. The data is not yet good enough to do this, but in the near future, it should be possible to test the area and no-hair theorems using gravitational wave observations. With many more gravitational wave detections expected, and the opening of a third laser interferometer, called Virgo, in Italy this year, I am excited by the possibilities this new era of gravitational wave astronomy will bring. The properties of black holes suggested that the area of a black hole is analogous to what is called the entropy in thermodynamics. Entropy can be regarded as a measure of the disorder of a system, or equivalently, as a lack of knowledge of its precise state. It would be a measure of how many states a black hole could have on the inside for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. In particular, I wondered, can one have atoms in which the nucleus is a tiny primordial black hole formed in the early universe? To answer this, I studied how quantum fields or particles would scatter off a black hole. I was expecting that part of an incident wave would be absorbed, and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole itself. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which expresses the entropy in terms of the area of the horizon. And the three fundamental constants of nature, c, the speed of light, g, Newton's constant of gravitation, and h bar, Planck's constant. I am proud to have discovered it. Later work uncovered the deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. This is called the Euclidean approach because it makes time become a fourth direction of space. The Euclidean space-time is smooth and contains no singularity at which the equations of physics could not be defined. It solved the fundamental problem that the singularity theorems of Penrose and myself had raised, that predictability would break down because of the singularity. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for more than 40 years and remains one of the most important unsolved mysteries of theoretical physics. Currently, I'm working with my Cambridge colleague Malcolm Perry and Andy Strominger from Harvard on a new theory based on superrotation charges to explain the mechanism by which information is returned out of the black hole. Information is encoded in an infinite head of supertranslation software on the horizon of the black hole. In an old village, we found a new road to go down. Watch this space. During the 1970s, I had been working mainly on black holes, but my interest in cosmology was renewed by the suggestions that the early universe had gone through a period of inflationary expansion, in which its size grew at an ever-increasing rate, like the way prices go up in the shops. In early 1982, I wrote a preprint proposing that the seeds for structures in our universe could be created by quantum effects during inflation. This was basically the same mechanism as radiation from a black hole horizon, except that this time it came from the cosmological horizon. I had used Euclidean methods earlier with Gary Gibbons to work out the temperature of de Sitter space. We held a Nuffield workshop in Cambridge that summer, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. Several people contributed to the final answer. This was 10 years before fluctuations in the microwave sky were discovered by the Kabi satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite. Today, the Planck satellite offers us a wonderful map of the temperature of the cosmic microwave sky, a snapshot of the universe, at less than 1,000th of its present age. The irregularities you see here are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse, to form galaxies and stars. So look carefully at the map of the microwave sky. It is a blueprint for all the structure in the universe. The cosmic microwave background continues to be observed, with better angular resolution and less noise, by experiments in Chile and at the South Pole, and there are also plans for another satellite. The original scenario for inflation was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state, but I thought this was unsatisfactory. Unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. What was needed was a space-time without singularity, like in the Euclidean version of a black hole. After the 1982 workshop in Cambridge, I spent time at the Institute of Theoretical Physics in Santa Barbara. I talked to Jim Hartle about how to apply the Euclidean approach to cosmology. According to this approach, the quantum wave function of the whole universe is given by a Feynman sum over a certain class of histories in imaginary time. Because imaginary time behaves like another direction in space, histories in imaginary time can be closed surfaces, like the surface of the Earth, with no beginning or end. Jim and I concluded that this was the only natural choice. We formulated the no-boundary proposal. The boundary condition of the universe is that it has no boundary. We had sidestepped the scientific and philosophical difficulty of time having a beginning by turning it into a direction in space. With my colleagues, James Hartle and Thomas Hertog, we set out to calculate what kind of universe would emerge from the Big Bang, according to the no-boundary proposal. It predicts our universe came into existence with a burst of inflation. It will start out almost completely smooth, except for the tiny departures predicted by inflation, which then give rise to all the structure in the universe we see about us. The irregularities in the observed microwave background agree with the specific predictions of inflation, combined with the no-boundary proposal. However, there is one key prediction of the theory, which has yet to be verified. According to inflation, a small part of the fluctuations in the microwave radiation can be traced to gravitational waves generated during the phase of rapid expansion. This part shows up most clearly in the polarization of the radiation. With the Planck satellite and other experiments, we are only in the early stages of measuring this polarization. However, new cosmic microwave experiments like the Simons Observatory offer real hope of providing firm and convincing evidence for this primordial signal. Actually, I have already lost a wager on this, so I am counting on the Simons Observatory to save my bank balance. Around the time of my no-boundary work, I decided to write a popular book. I thought I might make a modest amount to help support my children at school and the rising costs of my care, but the main reason was because I enjoyed it. While I was writing it, I visited CERN, and I became critically ill with pneumonia and lost my voice due to a tracheostomy. But I kept putting a lot of effort into the book, because I think it's important for scientists to explain their work, particularly in cosmology. I never expected A Brief History of Time to do as well as it did. Not everyone may have finished it, or understood everything they read. But they at least got the idea that we live in a universe governed by rational laws that we can discover and understand. There are many ambitious experiments planned for the future. We will map the positions of billions of galaxies, and with the help of the latest supercomputers like Cosmos, we will better understand our place in the universe. Perhaps one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on black holes and the state of the universe. It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe, is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do and succeed at. It matters that you don't just give up. Thank you for listening.